Good morning, everybody. We're going to be looking at some exponential equations today, a little bit more growth and decay, but we're going to hone in more on the mechanics of how that stuff works. So an exponential equation, kind of to review what we talked about last class, is an equation where your variable is an exponent. And so there's really two ways that you can solve an exponential equation. And they are that you can graph both sides of the equation. And we've looked at that a little bit before. So you graph the left side, you graph the right side, you figure out where they intersect. And the other way that you can do it is use what's called a logarithm. So a logarithm may or may not be new information to some of you all. I'm going to talk about it like it is. If you know what I'm talking about, that's cool. If you don't, that is also fine. So what a logarithm is, and so this is the math definition. A logarithm in base A of B is the power that A must be raised to in order to obtain B. Now, if you heard that and you were like, what on earth, Mr. Price, did you just say? So basically what a logarithm is it is the answer to an exponential equation, or it's an answer to an exponent. So like for example here, 2 to the third power equals 8. So what that means right there, so the way you read this, log base 2, the subscript there is a base. So log base 2 of 8 equals 3. So let me show y'all something real quick. So let me pull up this calculator. So if you go to math right here and you swing over to where it says log base, I never know what base is in all caps. I feel like I should say it loud since it is log base. So you hit log base and it goes 2 to 8. So log base 2 of 8. This is saying 2 to what exponent is going to give me 8. And that is 3 because 2 to the third power is 8. And where logarithms come in handy are when you've got questions such as, so like let's say it was 2 to the x power equals 10. So what do we have to multiply 2 by? Or how many times do we have to multiply 2 by itself to get 10? And if you look, it's kind of problematic because 2 to the third is 8, but then 2 to the fourth is 16. So we could infer that the answer is somewhere in between 3 and 4. We could infer that, but we don't know it for sure. So what we're going to do is we're going to use a logarithm. We're going to say log base 2 of 10 is my exponent. So 2 to what power will give me 10 is what a logarithm is going to answer. So we're going to say math. We're going to go down to log base. 2 to the 10th power is, so 3.3219280. And just to prove that to the 3.2192895, Mr. Price messed something up. What did he mess up? Oh, that was dang it. I was off. I apologize about that. To the 3.321928095 does in fact give you 10. And so what we're going to do real quick is we're just going to practice rewriting some logarithms. This is going to be a valid way for us to answer these. So 2 to the fourth equals 16. We're just going to write these as the equivalencies here. So if we've got a to the x power equals b, the equivalent form in a logarithm is log base a. So whatever the base is the base of the logarithm. And then the thing that's different is we're trying to figure out what the base to what power equals b. So let's rewrite a couple. So if this were here, 2 to the fourth power equals 16, the equivalent logarithm would be log, so that the base here is 2, so this is going to be base 2, of 16 equals 4. And you can always check those using a calculator. Back in the day, they used to have a book full of logarithms, and if you ran into where you'd have to use a logarithm, you would consult the big book of logarithms. Now we have calculators, we have computers, so we don't have to do that as much. So let's work backwards. If we know 3 to the 20, or 3 to what power gives us 27, that says 3 to the third power gives us 27. And our math statement should make sense here. 3 to the third power equals 27. It does. So we're good to go. That's kind of a way you can make sure that you're rewriting those. So then if we had 3 to the x power equals 10 and we wanted to figure out what that value was, we would say log base 3 of 10 gives you the x power. That will tell you that power right there. And if we wanted to go backwards and say, okay, log base 3, so 3 to the first power will give us x. So if that would say 3, the exponent there is going to be 1 equals x, and so x would just be the value of 3. So I don't need you all to know a ton about logarithms other than just how to rewrite it as a logarithm for today. That's as deep as we are going to get. So let's use this to actually solve some equations first. So to solve by using a logarithm here, what we're going to do is we are going to isolate our variable, and then we're going to rewrite it as a logarithm and solve it. So for example, if we have 3 to the x equals 7, the way I'm going to rewrite this is I'm going to say log base 3. So then the answer is, we're going to say 7 equals x. And so if we look at this, we go with math, I go down to log base. We're going to say 3 to the 7th. And I'm just going to round that to 3 sig figs. So we're going to call that x is equal to 1.771. And that is our answer. Now, the thing is, if you're looking at the examples in the book for this, you're going to see that they do it by graphing. We've already looked at doing stuff by graphing, so Mr. Price isn't going to necessarily go over that in the notes. I'm giving you all another tool to work with exponentials. So then on the second one here, we've got 3 to the x power plus 5 equals 50. Well, before we can rewrite this as a log, we need to have it to where it's just the exponential part by itself. So Mr. Price is going to subtract 5 from both sides here. We're going to get 3 to what power equals 45. And that's not going to work out perfectly. So what we're going to do is we're going to rewrite that using a logarithm. Log base 3 of 45 equals x. And again, we're going to come in here. I'm going to go to math. I'm going to go to log base 3 of 45. And that's going to be the x equals 3.465. 3.465. So let's look at one more of this type of problem. So we've got 60 plus 10 times 1.5 to the x equals 80. And the thing I need you all to understand, the only thing that's the exponential part is this part in orange. The 10 is not a part of that exponential. It does not have the x on it, so it's got to go as well. So what we're going to do is say, all right, I'm going to subtract 60 from both sides here, get rid of that first. 10 times 1.5 to the x equals 20. So then to solve this, I'm going to divide both sides by 10. And when you get to this part where you're like 1.5 to the x power equals 2, oh, I don't know what that is. That is not a perfect power, Mr. Price. That is usually a sign that we need to use a logarithm. So we're going to rewrite this. We're going to say log base 1.5 of 2 equals x. We want to figure out what is that exponent that's going to make that work. So I'm going to go to math. I'm going to go to log base 1.5 to the 2. And the exponent that's going to make that work is 1.71, if we round that to 3 sig figs right there. So logarithms generally just act as a way. If there's an exponent that we do not know, it's not a perfect one like 2 or 3 or 4, it's not a whole number. Logarithms act as a way for us to figure that out. And so with that is solving exponential equations. We're just going to use a logarithm, and we'll get more into logarithms on later during the week. So then the next thing that we're going to look at today is we're going to look at growth and decay. And you're probably like, Mr. Price, we've already looked at growth and decay a lot. And I'm like, yeah, we have. But I think the best way to get a concept down is to keep looking at it. So just to make sure that we've got it. So let me look at something here real quick. So with growth and decay, the general formula for growth and decay is that we've got some y equals k times a to the x plus c. And you're probably like, well, that looks a lot like the equation we looked at in the last class, and they're very, very closely related. So for growth, if things are going to be growing, the thing with the exponent on it, a, has to be greater than 1. You think about multiplying by like 2. If you keep multiplying something by 2, it's going to increase. If you multiply something by 3 or 1.1 or anything bigger than 1, that's going to be exponential growth. And so typically you'll see exponential growth in populations and the appreciation of assets. And then you'll see decay when that a value is between 0 to 1. If it's like 1/4, you're cutting something in fourths each time repeatedly. And you'll see that a lot in like radioactive substances, so like carbon dating or just radioactive decay in general. The cooling of objects. So if you've got like something hot and the cooling of that, it loses heat very fast and then slowly levels off. And also depreciation, which we've talked a little bit about as a class. So with that, again, just want to communicate this. So population, if a population grows by 20%, that is adding to your original value 20%. The assumed value is just 1 or 100%. And so if a population decreased by 20%, that would be 0.8 or 8, and that represents 80%. Let me just write that. Means 80% means 120%. That's just to help us out a little bit. So we're going to look at a couple of examples on this, and then we will call it a day. So the first example we're going to look at here, so we've got an entomologist monitoring a grasshopper plague, and notices that the area affected by these grasshoppers is given by A of n equals 1,000 times 1.15 to the nth. So 1.15, so it's increasing 15%. And it says n is the number of weeks after the initial observation. So n is the number of weeks, so it's increasing 15% a week. So we want to try. So we're given a couple things here. We want to find the original affected area. So if we want to find the original area, ask yourself real quick, how much time has passed if I'm trying to find the original? So you should be saying to yourself, well, Mr. Price, that would be n is 0. So what we're going to find a of 0. So that's going to be 1,000. We're going to be using this equation right here. Let me just make that pop a little bit. So 1,000 times 1.15 to the 0 power. Anything to the 0 power is just 1. So that's going to be 1,000 times 1. So that would be 1,000 hectares, which is some sort of land measurement. Mr. Price isn't exactly sure how much a hectare is. And so then we can also find it with this model after a certain amount of time, like 5 weeks. For 5 weeks, we would just be evaluating A of 5 times 1.15 to the fifth. Mr. Price do not be knowing that one off the top of his head, so he's going to be using a calculator. So A of 5, so after 5 weeks, 357 hectares. I guess we would have called it 2010 hectares if we were rounding to 3 sig figs, excuse me. And then for A of 10 here, for finding it for 10 weeks, we're gonna do the same thing. So then let's see, that's gonna be 1,000 times 1.15 to the 10th, and that's going to be 1,000 times 1.15 to the 10th. If we round that to 3 sig figs, that's going to be A of 10 is 4,050 hectares. And so the next thing here, so Mr. Price did not give himself enough time or enough space to graph this. We will have one where we will graph it. But so we want to draw a graph of the affected area over time. So basically we want to look at this graph. So Mr. Price is going to clear a place to graph this. 1,000 times 1.15 to the x power. And let's take a look at this graph real quick. Yeah, I'm going to have to mess with my window real quick. It is not large enough right now. So I'm going to go to my window real quick. So we're going to set the x-min to 20, do steps of 2. The initial population is 1,000. We've seen it gets as high as 4,000. Let's have it go to like 20,000, and we'll go by 1,000s. And so that graph right there, you can see this like smooth exponential curve that we've got. And you can look and get any points on this thing. So like after 20-ish weeks, it would be 18,000 of that plague, and so on and so forth. And so then the last thing that we want to do is we want to use our graph or technology to figure out the affected area. So we want to know, when is this going to reach 8,000? So the two ways that we could do this, we could set 8,000 equal to another part of our graph. And we look at that graph and we see this model is going to hit 8,000 at that point right there. So at that point right there, we say n is 14. We're going to call that 0.9 weeks. But if we wanted to use a logarithm, kind of just to show both sides of this coin here, we're going to take that original equation. We're going to say 8,000 equals 1,000 times 1.15 to the n, and we can solve this and get the same exact thing. So to do that, we're isolating this thing right here. We're going to divide both sides by 1,000. Divided by 1,000, we're going to get 8 equals 1.15 to the n. To solve this, we're going to rewrite this as a logarithm. Log of 1.15. Base is the base, and then to what power gives us 8? Let's find out. So we go to math, we go to log base, 1.15 to 8, and gives us the same thing, 14.9. If we round that 3 sig figs. So you can see graphing it or using a logarithm, either way works. It's really going to be a matter of preference. What do you prefer to do? What is quicker, for you? So then our last example today, we're going to look at example 6 on page 196. And we've got a diesel electric generator being switched off. And as it switched off, the current dies away. So it stops putting out current according to this model right here. So if what we're multiplying by is 0.25, if 25% of its value is remaining, it's decreasing by about 75% each time. So we've got where T is the time in seconds after the power's cut, and the I is the amps here. And so we want to find I of T when it's 0, when it's 1, when it's 2. And so looking at this, let's see, we've got I of 0 equals 24 times 0.25 to the 0. We've got I of 1 equals 24 times 0.25 to the first. We've got I of 3. I guess I should have done 2 first. Excuse me. 24 times 0.25 squared. And then we've got I of 3 equals 24 times 0.25 cubed. And so Mr. Price, real quick, is going to look at those. 24 times 0.25 to the 0. That's 24. Let's see, second enter. I'm going to do the first one. That's going to give me 6. Second enter. I'm going to punch in the second power to get 1.5. And then second enter. Oh, goodness, Mr. Price. Second enter to the third power, and that's going to give me 0.375. And again, those are all amps. That is the unit of measurement. What a terrible 6 that was. These are all in amps. We're amped up. So then on the second question here, it's asking what was the current flowed into the generator at the instant it was switched off. So how much is this generator getting the second it's switched off? And so you have to ask yourself, what would the value of time be the second it was switched off according to this model? So that time should be, time should equal 0. So then that means that I of 0 should work. So that means that 24 amps is the amount that should work. So again, when we're graphing, we can use these points that we generated here to find and identify a graph, figure out a pattern, and so on and so forth. So what we're going to do is we're going to use this data to draw a little sketch and use that sketch to try and predict how long it will take for the current to reach 4 amps. So we've got 24 amps at 0 time. So I'm going to do time as my x-axis here and amps as my y. So 0, 24, that's a dot there. Let's see, the next one we've got 1, 6. So there's a little bit of a steep drop off there. We've got 2, 1.5, so that's going to be pretty low down there. 0.375 is going to be even lower. 4 is going to be somewhere even lower than that. So we get this graph right here. And we want to say, okay, well, 4 is going to be pretty close to 0. This graph has an asymptote at 0, so it won't exactly be 0. So let's see. We want to figure out how long it will take for it to be 4. So I don't feel confident with my graph, just my sketch of using that to predict. So I'm going to use this model function that we were using earlier. Mr. Price's graphs. If your graph is good enough that you feel like you can do it, go for it. Mr. Price's graphs are not like that. His graphs are not nice. 0.25 to the 4th. So let's see here, to the 4th power. So the amount of time, or excuse me, how long will it take for, oh, Mr. Price, Mr. Price, what are you doing? That was not what the question was asking. Guys, I apologize. I got lost in the math sauce and was just being a robot. Please, I apologize for wasting your like minute of time there. We want to know how long it's going to take for it to reach 4 amps. So what we want to know, amps is I of t. So we're going to set that. We're going to say 4 equals 24 times 0.25 to the t. I apologize about that, you all. And so we're going to solve this using a logarithm. So I'm going to divide both sides by 24. So we want to do 0.25 to the t equals 4 over 24. And we're going to use a logarithm here. This is going to be an ugly logarithm, but it's still going to work. So we're going to do log base. So log of 0.25. So 0.25 to what power gives us 4 over 24. 0.25, 4 over 24. And let's see. So that's going to be 1.29. T equals 1.29, and that is seconds. Again, I do apologize about that. Mr. Price is being sloppy, but we got there eventually. So that in a nutshell is what we've got for today. Solving exponential equations, applying those exponential equations to solve for different models and whatnot. So if you all have any questions, please let me know if there's anything I can do to help clarify something. And I hope you all have a good rest of your day. Bye.